I want to talk about the properties of the K-moduli. So let me first state the theorem. I mean, the theorem was proved in 2021, combining lots of previous work together. I'll explain this in more details, but let me first state the theorem. So if x0 to c0, so here c0 is a puncture curve. C taking out 1 point is a family of K polystable final variety. Then, I mean, of course, after possible base change, one can extend x0 across this point such that x0 is also K polystable. So basically this, I mean, as we know, this essentially implies the properness of the K-moduli. So let me, before I talk about the proof, let me give some remarks. So if the fiber is smooth, then this was known by analytical method, by some Riemannian geometry. Done by Donaldson, Sung, and also later there's some a log smooth version by CDS, Chen, Donaldson, Tian, and many other people. But so far, I think they still need a smooth assumption, and a version of a single version is still under development. And the second remark I want to mention, I mean, here I say existence, but the uniqueness was worked in, I mean, well, in this talk, I mean, these are my collaborators, so I just use the initiate for their name. 2019, we show that the limit is the K polystable limit is unique. I mean, often you can have more than one final limit, but if you post a K polystable assumption, then it's unique. And the third remark I want to mention is that, I mean, of course, in the KSBA case, KSBA case, this was essentially implied by MMP. So, I mean, you know, in practice, if I want to study the KSB moduli examples, it's still very hard to find the limit. But if you are an MMP theorist, I think this gives you a pretty satisfying answer. However, the final story, the limit is more complicated. So now I want to sketch a little bit about the proof. And then I will talk about the new proof. I mean, replace some part of this. So the proof essentially contains two parts. So the first part is the flowing theorem that if so we can define this delta x, the stability invariant, to be the infimum of AXE and SXE. Here E are all divisorial valuations over X, so Y to X is birational. And you look at the ratio of these two invariants. Here X is always a final variety, so maybe I should write here. Now X is a single variety, it's not the family. Then the theorem say that when delta x is less or equal to 1, actually you can go a little bit higher, and we really just need the delta x less than 1 case. But the proof are all the same, is that then the delta x, Okay, sorry. That's always, yeah, okay. I can do. So AXE is just the log discrepancy. So basically, this is discrepancy plus 1. And the S is going to be the 1 over minus kxn integral, if I call this f upper star minus kx, the volume of this minus te, and the integral dt from 0 to infinity. But actually, you just integrate to the pseudo-effective threshold. I mean, of course, the A is some familiar invariant, but S is kind of, I think, very, very novel invariant, which I think of first found in the work of Fujita and Ji. So basically, the theorem say that you can tell whether X is stable just by looking at this invariant. If this invariant is less than 1, if and only if the X is unstable. So you somehow turn the original definition of K stability into the, just look at the number of this, the stability threshold. And okay, so, okay, delta is defined as an infimum, but the theorem say that when delta less or equal to 1, then the delta is actually computed. For some E. So I'll explain the proof of this a little bit because we somehow need it. So this is a step A. So maybe let me call this part is, this statement is the theorem A, and even this theorem has several recipes to prove it. The first part, there are 2 treatments. The first one is by Bloom, Liu, and myself in 19, is that we show basically there is a cosine monomial minimizer. V, which is, so when I say minimizer, I just mean you can compute this. So you can easily extend the definition of A and S to the more general valuation, like the cosine monomial valuation, and which is a LC place of a Q complement. I mean, if you don't know this, what LC place of Q complement, I mean, I don't need it that much for now, so you can just ignore this. But there is another treatment prove something similar, but this is by combining a work of Bloom and Janssen, 17, and myself, 19. So we basically show this. I mean, this looks weaker than this, but that's some statement that we need later. So that's why I want to talk about it. So basically, let's say that the Bloom-Janssen say that there is a generic limit construction yields the minimizer. So here, this generic construction, generic limit construction doesn't need this assumption, delta x less than 1. But it yields a minimizer, and then I prove that we'll combine with their work, we prove that which is cosine monomial. So we prove this is cosine monomial. So this is the first part of to address theorem 1, theorem A. Now I want to go to the theorem 2 part. Let me just, so So this is. Well, you need, but I'm not going to explain. I'm not. So, I mean, if I say it's a Bianca valuation, does it help? Okay, I can explain that, but then I might not be able to finish my lecture. So I consider a log resolution y to x, and I look at these component of bunch of intersection of this, and now I choose a number which is larger than, which is have a non-negative coordinates, and I define V alpha f is basically the minimum of the pair of alpha beta. So here I consider that the f, I expand it around the generic point by using the coordinates of this, the beta. So here, z and beta are just tuples. So then I just look at all this, sorry, there's a coefficient here. I consider all non-zero them. So basically it's a monomial valuation after pullback. That's why it's called cosine monomial. And you put all of them together, that's all the cosine monomial valuation, which you can prove it's the same as a Bianca valuation. So basically you can regard the divisor valuation as a rational object in here. But these are the real one. But this real one is not a complete space. You have to go to the valuation space to make it to be complete. So then the second part is some statement I first prove with Yu and Chenyang, and then we have a stronger result 1 year later is that there are two statements. First is that V is actually LC place of special complement. I'll explain what the special complement means. And the second part is that this implies that the GR, VR is finitely generated. So here R is a coordinate ring of the Fano variety. So let me just say that the complement, I mean, this is really important to say special. For instance, if I consider valuation, which is not necessarily divisorial, if I only know it's the LC place of a complement, then the function generated could fail. So if it's divisorial, then it follows from BCHM that the function generation still works. But if it's in general cosine monomial, we need to think something more special. And recently, my student Ziyuan Chen had a better understanding of this step. I think the paper is coming out in 1 week or so, hopefully. You mean X? Well, so what special here means that you basically there is a, let me just say roughly speaking, there is a complement, but basically it's a complement D larger than epsilon G. Here G is some divisor in general position. I mean, what we need is slightly more specific than in general position, but you can just roughly think about this. So basically, they say that the V is not just an LC place of a complement. It's actually an LC place of a complement which can contain some general position divisor or even any divisor. So that actually, if you think about this, let's basically just say that this LC place, the complement is naturally satisfies some kind of like tie break. So, but here it's not a divisor case, it's a cosine monomial case. But somehow this information of tie break was built into the fact that it's a LC place of some kind of basis type divisor. But this fine generation is the part one. And the part B is completely different, and is something we try to give a new proof today. But let me just first explain this, that the part B basically say that there is a theta stratification on the stack of all KLT final variety. So yesterday when Kristen talked about curves, she said that it was not clear to me what's a large stack contain all the smooth curve and all the limit. But in the final case, I think it was clear. I mean, it is clear to us that we should just consider all the KLT final variety. That works pretty well for all the questions for now. So particularly every fiber is normal. That's something very special for the final case. So, but what's this theta stratification? I'm really not going to talk too much about this, but let me just say that this is some notion I think introduced by Harper-Leisler. And so basically, this theta stratification just say, roughly speaking, any K unstable funnel, there is a unique GM degeneration which maximally destabilize X. So this X0 is degeneration. So this uniqueness, of course, after reparametrization. So this is very much like the vector bundle case that you consider the Harder-Nahrschman filtration, and the degeneration will give you the degenerate of X to the direct sum of all the gradient piece. And here that the funnel, you also have a unique maximum destabilization if your funnel is unstable to start with. So that's not enough. We need that, but that's not enough. I'm going to explain this. I mean, naturally you want that delta to be minimal along the degeneration, but if you only ask delta to be minimal, I mean the uniqueness is not satisfied. So you need to even refine this. So basically, in a paper, Bloom, Liu, Harper-Leisler, and myself, 2020. I mean, that time we work under the assumption that the step A holds, but now since we already have it, so we don't need. That's how it works. So basically, we just construct the maximum destabilization. Of course, assuming step A. So what's this minimizing? So basically, we look at the test configuration, special test configuration, such that we wanted minimizing the following function. The function is the Fataki of the X divided by the minimal norm of this test configuration. And so this is basically the A divided by S minus 1. So this is basically the same as, roughly speaking, the same as minimizing A over S. But as I said, there is usually more than one, because this is like some kind of minimizing linear question. So then we have to design the thickened function to minimize. And we put an alphabetical order on that. So we basically look at all the minimizers, satisfy the first one, and among them, we look at the minimizers, satisfy the second one. So basically, all the minimizers, the first one will force your final variety live in a bounded space, and the question turns similar to a GIT question. And then the norm becomes a GIT norm, and we know that for quadratic GIT norm, the minimizer is only along one direction if there is one. That's by Kempf. So that's how it works. So basically, we show that they satisfy all this axiom of Theta stratification. But of course, you still need this is M, minimal. That's something they call minimal norm. Yeah. Second one is just 2. That's L2 norm. L2 norm. I mean, so then you still need this abstract step that the Theta stratification imply Properness of K-moduli. So this is some idea, some theory developed by Harper-Leisler in his thesis. And then I think I really like the written up in the work by this great work by Harper-Leisler and Henlos. So if you put all of them together, you get the Properness of the K-moduli. And this part, I think you can regard it as kind of abstract lanton method. So basically, lanton has a way to prove the moduli space of vector bundle is proper without using GIT. But if you go to this, try to abstract lanton's argument, that was this part of the theory. And that was exactly what we want to understand by concrete lanton method. So we really want to develop a more concrete lanton method in the final case. So that's what I'm going to talk about next. So today, we want to, as I said, replace abstract lanton method by explicit lanton method. So what I mean, so this is a theorem. I also hope which can appear online in a week. Hopefully. Yeah. So we consider, again, this is X over. So we can first compactify the family such as the central fiber is KOT final. That how we understood it like 15 years ago by my work with Chile. So the only thing is that if you start with semi-stable generic fiber, this way doesn't tell you that the central fiber is semi-stable. So you have to replace your central fiber, gradually increase the stability. That's what we want to do. So basically, this is a family of KOT final variety. And so one family, of course, I mean Q-Grostin, locally K-SPA, it's the same thing. That I assume that the central fiber has less stability than the generic fiber. And it's also K unstable. So it could happen, both of them are K semi-stable, but one still have a large delta, but that doesn't really matter with us. So in this case, we're interested. Then we show that there exists a divisor E over X over this family such that minimizing a relative version of delta function, which I'm going to define next. But this is some new concept we introduced in this paper. And such that after, again, of course, I'm always allow, after base change, we can, then there exists a X prime over spec R, such that first the X0 prime essentially just corresponds to this divisor E. So basically, it's like a two-ray game. You extract this E, and you contract the original X0. You get a new family of Fano variety. So, and the delta X0 prime is larger than delta X0. So you increase your delta. And we know that the delta can only take Feynman values in our case. Then after Feynman steps, this process is going to terminate. So somehow, we want to replace this kind of abstract lanton method by a concrete construction which finds some E, which minimizes some function, and then such that, and show that this E will give us the replacement. Again, I mean, theoretically, this is, explicitly, this is still going to be quite a difficult process to find the limit. But I think theoretically, the bilateral geometers are happy with this construction.
So you can these E maps to the central fiber, right?
Yeah, E maps to the central fiber. Okay, so maybe I should say E over X0. X0. Okay, I don't know. I mean, yeah, E maps to the central fiber. Sorry. No. I mean, again, theoretically, we construct it exists as a minimizer of something, but in practice, I think it's pretty hard to find this E, to find this E explicitly. I mean, like, we have this optimal discretization in the absolute case, but actually, in practice, when people study explicit case stability, to find the E which like minimizing this delta function. I mean, I think that's probably, you need a lot of working experience to do that. And then you use something like Abban-John method and a bunch of other methods to do this. But in practice, you don't follow this like theoretical way. You have to build up your understanding of the explicit Fano varieties and then argue. Actually cleverly argue. But this we just have some like theoretical solution. Mm-hmm. No, I don't expect that. Yeah, I mean, again, if you just minimize this type of delta function, that's like a minimizing a ratio of two linear function. Usually, the minimizer hit a face of the polyhedron. And so if you want uniqueness, you have to add some extra data there. Yeah, but I mean, so we don't care about uniqueness that much in this work because anyway, in K-polystable situation, we already solved the uniqueness like many years ago with Harrow. So here we mainly care about the existence. So I'll give you a sketch of the proof, and then I'll go in more details about proof, depending on the time I left. So I want to first define what this relative delta invariant. So it has to be a family. So the first version is somewhat quite simple. That if I consider, I first need to define the delta m, the finite level of this. So this is defined, and I have a parameter c here, and I define that this to be the delta m for x1 minus c x0. I mean, I put a c1 minus just for some, not so obvious reason. But later I will just call this divisor to be delta. And I basically look at the infimum of this pair for among all the LCT with respect to all the m basis type divisor. So this infimum goes on all the dm. But here, dm is of the form that 1 over m nm. So nm is the dimension of h0 minus kxt, just the dimension. And so this is standard part. But now I require that the divisor of Si. But here the Si, all of them, form a R basis. So in the absolute case, the base is a field, so this is just a vector space. But now it's a module over this dVr. So we need it to be R basis of m star minus kx, which is the equivalent to say that when I restrict this section on the central fiber, it gives me a basis of the vector space on the central fiber. So now I look at all possible dm like this, and I compute the infimum. That's delta mc. And then one can show that the delta c, is going to be the limit. I mean, the limit exists. You need some argument, but it's the same similar as before. And also you can show that this guy is the same as the infimum of ax delta e divided by se. So here, se is really, I just computed this as for this filtration induced by E, but on x0. So the S is still some calculation only on the central fiber, not on the module. And the FE on H0 kx0 is just going to be the image of the F lambda E. So you look at the vanishing order of your sections has at least lambda along this Rm. So maybe I call this module Rm. And then it has a map to Rm. By first put it as a submodule of the curly Rm, and then map to this Rm. So Rm is this guy. Sorry, Rm, maybe I didn't write it. Rm is, this guy is Rm. So that's just the m's piece of the central fiber. And so here, when I say this relative delta invariant, I will show you that we basically choose a very small surface C, and then that works. So basically, I want to show that under the assumption that delta x0 is less than 1 and delta xt. So here, these are just two absolute delta invariant. Then, first, there exists a divisor E over X over the special fiber. Maybe let's say over. This is what Joaquin asked. It's really over the 0, and together with a family, which yields X prime such as basically x prime 0 bidirectional to E. So this is, again, the first this part of this divider. And so here, okay, let me just make assumption that C is sufficiently small. So we choose C to be positive, but sufficiently small. And then we want to show that, first you look at the delta x0. This is a central fiber. It's easy to show that this is actually the same as delta 0 x0. Delta 0 x. Because, I mean, you can roughly thinking that if I choose C, where is my, okay, here, that's right. If I choose C to be 0, then when I compute the LCT, it's essentially just compute on the central fiber by inversion of a junction. So there is no difference to compute for xx0 or around the special fiber. So these two numbers become the same. And but of course this guy is the minimum among all the E. So if I look at the place E, of course it's less than AX delta E over SE. I mean the S part doesn't change, but you somehow just replace the AXX0 to AX1 minus CX0. So you decrease the coefficient of your central fiber. Because E is over the central fiber, the log dispersion increase a little bit. So this number straight increase. But as my assumption, this E compute delta CX. So far, every step is, once you have this E, every step is straightforward. But the key estimate is that this guy is actually less than x0 prime. So somehow the relative version is smaller, or is at most the central fiber of the replacement. So somehow let me just say the crucial estimate lives in this inequality. All other steps are straightforward. So now I have about 12 minutes left. So I'll very quickly So now I want to talk about the divisor minimizer. So again, this is very similar to the question I had at the beginning in the absolute case, that I want to find this E such that A over S compute this delta. But now this is the relative case. So we just follow the path of the absolute case. But there are several technical places we really have to introduce some new techniques. So again, we follow the first step, we follow this generic limit construction step. So we have this F. So we choose a sequence go to minimizer. So we choose the EI such that the A over S in this case go to the infimum, and then we show that it admits a generic limit F. And then, so here, for this generic limit exists, we have to assume our base to be complete. So basically, this is the relative version of the generic limit construction. And then, again, we can just use the theorem that there exists a cosine monomial minimizer V compute the LCT of the base locus of this filtration, and then you can show that the delta x is given by A x delta V divided by SV. So this way you find the comonomial valuation, and at least, I mean, if under this assumption, then you can just restrict your comonomial valuation back to, so you first need to take a completion and then restrict it back, you get a valuation over the original family, which still computes the minimizer. But to prove the finite generation, some question? I mean, that step is not so different with the previous ones. But to prove this minimizer is finite generated, that was actually somewhat tricky. So basically, let's say, okay, maybe I'll just skip this part. I don't have time to talk about it. But let me say that it's harder to show that the GR, so basically V is LC place of special complement. So once you have this, then you can just apply the hierarchical finite generation to still conclude the finite generation. But to show that the V is actually LC place of some special complement, this step is significantly harder than the absolute case, and you need some new tricks to deal with it.
Sorry, so here you got that V is just a quasi-monomial valuation.
That's right.
A posteriori, you get that V is actually divisorial?
No, I mean, the story is once you know the finite generation, then you know any nearby divisor valuation also minimize it. That's right. But you need the finite generation to conclude that. That's right. There is a phase containing this quasi-monomial one as the minimal rational phase contain this. That's right. The minimal rational phase contains this quasi-monomial one. There is a small neighborhood in this. But you need the finite generation to conclude that. That's the point. That's why the finite generation is important. So then I'll skip to discuss this. Hopefully, you can read this on archive maybe in a week or so. But let me talk about the increasing of the delta invariant. Because this is somewhat mysterious at the beginning. So I said, why do you have this inequality? I mean, so let me see. We have this two model. Once we finish step one, we have this two model over C, which is spec R. And I can assume Y, which is just basically the two-ray game. In this case, that Y extract E, and then there's a birational contraction, contract the birational transform of X0 to get this family. And so basically, let's say P extract E, and the E is birational to X0 prime in the divisor. And remember, E now is given by the minimizer. So let me say E is a minimizer of delta X. But to explain the ideal, let me first assume that we assume that E indeed actually computes delta M X delta. So we will say that the delta M increase. And then I'll explain how to pass from delta M to delta. Ooh. So let me first explain what happens in the finite level. So let me say that delta M is equal to, I want to say this is less than delta M X0 prime. So, okay, now we look at what's delta M X prime. delta mx prime, we know that by the original definition of Odaka, Fujita Odaka, this is the infimum of the log threshold of x0 prime dm. So here dm is the basis type divisor, m basis type divisor of h0 minus kx0 prime. I mean, this is the original definition. But there's a simple trick, I think first observed by Aben and Zhuang, is that, so if I compute a basis type divisor, I can require over vector space, I can always require this basis type divisor to be compatible with the second filtration. So basically, because any basis type divisor works here, so I can just look at the LCT of x0 prime dm. But now dm is still basis type divisor, but I require that the dm is, sorry, dm prime is compatible with the filtration induced by x0. So now I regard x0 as something over the x prime, as some divisor over the family x0 prime. So that will induce filtration. Now I restrict on this x0 prime. So these two LCT are the same. That was Aben Zhuang's observation. And but by inversion of a junction, this is just the same that at the infimum of LCT. Now I lift x0 to the pair x prime, x0 prime. And I lift this dm to be the divisor dm prime, such that the dm prime now compatible with fx0. So now I don't restrict. This is over the generic family. So here, again, when the coefficient is 1 along the central fiber, it's the same when you compute over the family or you just restrict on the special fiber. That's the power of inversion of a junction. So no matter how you lift your divisor, the LCT will be the same. And here we just to lift the weight such that the lifting is still compatible with fx0 prime. And then we know that if I look at the birational transform, the dm0 here are kind of horizontal divisor. So I can just look at the, okay, maybe I should put a tilde here to mean it's a family. And now the dm tilde prime, I look at the birational transform, which is dm on the family x now. So the horizontal divisor, now instead of looking on x prime, I look at on x. And it was a simple observation that this is still a m basis type divisor with the extra assumption that this is compatible with fx0 prime. So, but then when you compute everything on x0, then it's just computed for the pair x0, 1 minus c x0 prime. So then you can say that this is larger than the infimum of LCT. I mean, here I need that the delta is less than 1 too, but you can easily see that this is less than, larger than the infimum of x 1 minus c x0 and this dm, such as the dm is any basis type divisor. So instead of only look at the comparative divisor with fx0, now we look at this, and of course the LCT will go down, and I think that's my. Okay, let me just explain using a little bit by words how you go to the infinite level. Actually, going to the infinite level is a lot more technical because you start with this E, and what's playing here? There are two numbers. In this case, they are the same, but the second number you want to look at is the delta m, lambda m, which is the infimum of just if I compute everything on ye, and the plus. So I look at this, and now I look at the birational transform of basis type divisor on X, and I look at the infimum of over all the dm. That's right. So for all this kind of basis type, I look at the birational transform, and I compute the LCT on this resolution, and I still want to show that the infimum of the lambda m is larger than delta x this. So I need to show this, and this will boil down to compare how Sm converge to S. But now instead of Sm, it's Sm minus the vanishing order along E times Se. And you want to control the persons of this persons converge to the S function. In the original work of Bloom-Janssen, they construct this concave body to construct this process. And you know that the S function is convex. Concave or convex? Okay, convex, let's say. And I'm always confused by this. So you need this like convexity of this function. So here you construct this concave body. The trick is we choose E to be the first coordinate of this concave body. And then that becomes a linear function. So then you have a convex function minus a linear function, which is still convex. And then you can apply the same argument. But we have to construct the concave body more carefully to treat this inequality. And putting all this together, we show that the delta increase. Thank you very much.